In this laboratory demonstration, we'll be looking at flow over hydraulic structures. In general, there are three types of flow hydraulic structures. These are, for instance, flow measuring structures like spillways, weirs. There could also be regulatory structures like gates. There could also be energy dissipating structures like steeling basins. And these structures find wide applications in civil engineering infrastructure. For instance, in the Val Dam, you have a reservoir where flow proceeds over a series of spillways onto some dissipating structure before it gets onto the adjoining stream, downstream. It could also be in irrigation systems where you have regulatory gates which will regulate flow from one area of the irrigation field to another. It could be a dissipating structure, for instance, in stormwater infrastructure, which allows for flow to proceed from a detention system onto a dissipating structure before the flow proceeds onto the adjoining areas. I'd like you to appreciate that we are looking at laboratory demonstration of flow over hydraulic structures, which are in real life situations or applications. These structures that we'll be looking at are flow over sharp-crested rectangular weirs, sharp-crested triangular weirs, broad-crested weirs, flow over gravity spillway, flow over siphon spillway, flow over dissipating structures, the steeling basin, the deflector bucket, the submerged bucket. This is the model of a rectangular sharp-crested weir. This weir is now being placed in the flume, and we will simulate the flow over this particular weir. Take a reference level, and that reference level is the crest of the sharp-crested rectangular weir. I'd like you to observe the unique shape of the nap, which is the flow downstream of the sharp-crested rectangular weir. It is unique to this particular weir. When the flow has stabilized, you should take the depth of water at an upstream location, and that depth is
49.69 millimeters.
49.69 millimeters. And as well as the discharge from your discharge meter, and the reading from the discharge meter is 8,399 liters per hour. I'd like you to take 5 readings of the upstream water elevation and the discharge using the discharge meter. And from those readings, ensure that in between readings, flow is steady, and the way that you will determine if the flow is steady is by ensuring that the dial meter in the discharge has now stabilized. Use these 5 readings that you have obtained from this investigation to calibrate the weir. What we mean by calibrating the weir is the discharge relationship in relation to the water level. With this discharge, with this rating curve, we would like you then to estimate what your discharge coefficient is, and as well as your exponent on the water level above the crest of the rectangular sharp-crested weir. I'd like you to comment on your results, the results being the discharge coefficient and as well as the exponent on the upstream head. Compare your results with those in the literature others have done the same investigations and published them in the literature, and I'd like you to make comparisons. Do not expect to have exact match between your results and those in the literature, and provide reasons why there are these discrepancies. You are simulating modular flow and submerged flow. I'd like you to make your observations, report on your observations in your laboratory report. And this relates to your downstream conditions. Ensure that you take careful observation of those downstream conditions and how they impact on the flow over the rectangular sharp-crested weir. Observe the flow as it is and report on your findings in terms of your observations. Right now, the tailgate of the flume will be raised, and I would like you to make your observations. Under these conditions, which are now totally different from the previous case, I'd like you to report on what you have observed with regards to the phenomenon, the hydraulic phenomenon, which has proceeded from the downstream area to the upstream point of the sharp-crested weir. The hydraulic structure model before you is the triangular sharp-crested weir. It is now being placed, it is a 60-degree sharp-crested triangular weir. It is now being placed in the flume. Take a reference height, and this height is above the notch of the triangular sharp-crested weir. The equipment has been turned on, and you can observe the flow over the triangular sharp-crested weir. It's important for you to observe the unique feature of the shape of the flow downstream of it, which we refer to as the nap. And this is unique for a triangular sharp-crested weir. The triangular sharp-crested weir accepts a maximum discharge, and that maximum discharge is dictated by the height of the weir above the bottom of the flume. When the flow has stabilized, you should take the water level at the upstream location, and its value is
72.21 millimeters.
The value of the upstream water elevation is 72.21 millimeters. Furthermore, you should also take the discharge from the discharge meter. Its value is 4,370 liters per hour. From the calibration equation which you have for the triangular sharp-crested weir, estimate the discharge coefficient and as well as the exponent on the upstream head. You will observe that the discharge coefficient and the exponent on the upstream head for the triangular sharp-crested weir is different from that of the rectangular sharp-crested weir. Your results for the triangular sharp-crested weir should be compared with those in the literature. Others have done the same experimental investigation and have reported their results. I'd like you to make comparison between your discharge coefficient and the exponent on your upstream head and those in the literature. Comment on any discrepancies that you will observe. This is the broad-crested weir, and the dimensions of this weir are given to you. This weir will now be placed into the flume. take the reference level, which is the height of the crest of the broad crested weir. Turn on the flow through the flume. Observe the unique features of the flow over the broad crested weir. You see a decreasing free surface elevation up to the downstream end when the flow becomes supercritical. It's important to point out that if the flow is too low, then the boundary layer impact of the broad crested weir on the flow will be quite significant. And you would like to avoid that because that affects your calibration equations. As you can observe, there is significant water elevation over the crest of the broad crested weir. When the flow has stabilized, you should take the upstream water elevation at the upstream point. And what is the value for that elevation?
65.44 millimeters.
65.44 millimeters. And as well as the discharge that is observed from the discharge meter. And that value is 10,308 liters per hour. The 5 readings for the broad crested weir relate to the upstream water elevation and the discharge. Note that in between readings, you should ensure that the flow is steady because the investigations that are being carried out are for steady flow. Use these readings to calibrate the broad crested weir. The calibrated equation will be different from those that you may have observed with regards to the rectangular sharp crested weir and the triangular sharp crested weir. The hydraulic model before you is the gravity spillway. We will observe the flow over this particular hydraulic model. It is now being placed in the demonstration flume. You will now be expected to take a reference elevation, and this reference elevation is the elevation of the crest above the bottom of the demonstration flume. Turn on the flow through the demonstration flume. When the flow has stabilized, take the water level at the upstream location, and its value is
46.96 millimeters.
46.96 millimeters. Also, take the discharge through the discharge meter, and its value is 8,717 liters per hour. 8,717 liters per hour. I'd like you to take 5 readings of the upstream water elevation and the discharge using the discharge meter. And from those readings, ensure that in between readings, flow is steady. And the way that you will determine if the flow is steady is by ensuring that the dial meter in the discharge has now stabilized. These 5 readings that you have taken for the gravity spillway can be used to calibrate the spillway. In other words, to have a relationship between the upstream water elevation above the crest and the discharge over the gravity spillway. The calibrated equation for the gravity spillway can be used to estimate the discharge coefficient for the spillway and as well as the exponent on the upstream head over the crest of the spillway. You should compare your results with those that are reported in the literature because others have done similar investigations. Your results will be different from those in the literature, and you should provide reasons why there are discrepancies between your results and those in literature. Before you are 3 hydraulic structures. They are all dissipating structures. They dissipate the energy downstream of hydraulic structures such as spillways and weirs. The first structure is the stealing basin with the baffled blocks. The second is the deflector bucket. And the third is the submerged bucket. We shall examine the flow and the dissipating mechanisms of these 3 dissipating structures. The deflector bucket is now downstream of the gravity spillway. Observe the dissipating mechanism of the deflector bucket. It is totally different from that of the stealing basin with the baffled blocks. Write down your observations in terms of the dissipation of energy by the deflector bucket. Downstream of the gravity spillway is the submerged bucket. Observe the mechanism for dissipation. You will observe at a low tailwater elevation that there is very little dissipation that takes place. However, the tailgate now will be raised and observe the phenomenon in terms of the energy which is dissipated by the submerged bucket. The hydraulic model which is before you is the Siphon spillway. It is a very unique spillway. It is a spillway which is used in certain circumstances where there is space constraint and the gravity spillway may not be appropriate. The Siphon spillway has the entrance there, the crest, the exit, and the hood. When flow proceeds through the Siphon spillway, you expect to have negative pressures at the crest and at the hood. It is now being placed in the demonstration flume. The reference height, which is taken for the analysis of flow through the Siphon spillway, is the bottom of the channel of the demonstration flume. I would like you to observe 3 unique features of flow through the Siphon spillway. The first of them will be weir flow, and I will have to carefully adjust the flow so as to show and demonstrate weir flow over or through the Siphon spillway. At the moment, there is no flow taking place. The reason is very simple. The water level is below the crest of the spillway. So I am carefully adjusting the flow until such a time when it is just above this, in which case then weir flow occurs. And weir flow is now taking place. It will transition very quickly to the second type of flow, which is aerated flow, and it's very unstable. And you can see how unstable it is in the sense that you have air bubbles which are now being entrained into the flow and passing through further downstream. This is still aerated flow because you still have air bubbles. And I need to get rid of all of the air bubbles so as to transition to the third type of flow, which is prime flow. It will take a bit of careful adjustment such that you can observe this third flow phenomenon. You still have air bubbles trapped in, which need to be expelled. And we are carefully increasing the flow so as to get rid of all the trapped air bubbles. This aerated flow is very unacceptable for the stability of the siphon spillway because it triggers vibration through the system, and it could, for a very large installation, lead to the collapse of the siphon spillway. There are still some air bubbles. I'm trying to get rid of them. All of the air bubbles have left, and now we have the prime condition. The siphon is said now to be flowing under primed condition. 2 water depths will be taken in this particular investigation of flow through the siphon spillway. The first will be the water depth just upstream of the entrance to the spillway, and this is referred to as the headwater depth. What is its value?
203.58 millimeters.
Its value is 203.58 millimeters. The second depth which will be taken will be at the exit of the siphon spillway, which is referred to as the tailwater depth. What is the value of the tailwater depth?
53.48 millimeters.
53.48 millimeters. You also need to take reading of your discharge from your discharge meter. Its value is 5,755 liters per second. You are expected to use these 2 depths, the headwater depth, the tailwater depth, to estimate the discharge through the siphon spillway and compare that discharge which you have calculated with what you observe from your discharge meter. This concludes the video on various demonstrations of flow over hydraulic structures.